For waiting for the stream. All right, I'm going to start the recording then. All right, anytime.
All right, we'll get started. I'm going to introduce today Dr. Victor Gensini. He's coming to us from Northern Illinois University, where he's also the Deputy Director of the Center for Research, Computing, and Data. He received his PhD from the University of Georgia, a master's in Northern Illinois, and a BS at Northern Illinois. So I guess he's back at his alma mater. He also is a guest faculty researcher at Argonne, which is the Department of Energy lab in Illinois. And he has his AMS certified, he's an AMS certified consulting meteorologist. So that, for those who are unfamiliar, gives the opportunity to do consulting work, for example, working with insurance companies, and in his case, in severe weather issues. So his research subjects broadly cover severe weather and climate, and we're looking forward to hearing his talk today on severe convective storms, the past, the present, and future. Take it away.
Awesome. Okay, make sure I'm unmuted. Good. Sometimes, you know, you Zoom, you'll start for 5 minutes and nobody will tell you that you're on.
Yeah, you're good. We can hear you.
Awesome. Thank you so much for the introduction, Angela. I sure wish I could be up in Madison today. You know, we're really only about an hour and a half in terms of driving distance apart, and be able to not only present to you, but share in a beverage after the colloquium. So I sure miss those in-person interactions, and look forward to hopefully making it up there sometime in the future. So the talk is probably, you know, the title is fairly descriptive. I don't think I have to go into too much data in terms of an outline, but I did want to keep this sort of at a higher level to appeal to a broader audience of looking at various impacts of severe convective storms, ranging to historical precedents, our sort of current state of the knowledge in terms of mostly prediction and analysis, and then some sort of cutting edge / I think future visions for severe convective storms. And we're going to focus mostly in this talk on tornadoes, although a lot of this applies to severe convective wind and also hail. If we have a little bit of time at the end, I definitely would like to discuss some hail. I've had some great meetings this morning with some of your faculty members discussing various aspects of research and possible areas for collaboration. One of the things I like to do any talk is sort of give you, instead of an overview slide of, you know, text, just give you a nice collage of what it like, I guess, a day in my life, everything from being a Purple Martin landlord here in the bottom to being out in the plains every year, traveling 15 to 20,000 miles, studying doing field work in relation to taking measurements for severe convective storms. And we have an exciting field campaign that we're proposing to NSF that is going to look at hail. But and everything in between. Of course, I'm a beer snob. I guess you could call me a beer snob. Not so much a coffee snob, but definitely a beer snob. And I'm a Packers fan, so I guess most of you in Wisconsin and Madison would be okay with that, I suppose, if you're native to Wisconsin. But I'm also, like many of you, very likely a huge weather geek. This is my annual Halloween costume for my synoptic meteorology class, and the students have told me that next year I need to up my game and add a dry line on my left leg here to really finish off, maybe put in some isobars too. That would be kind of cool. But you can tell I'm a pretty big weather geek. I teach synoptic meteorology, our PhysMet radiation and thermo courses at NIU, and also programming for atmospheric science. So like some of you probably, I got interested in atmospheric science. In my case, was a significant tornado event that actually hit my high school. And I was on a path for engineering at the time, and really never looked back after this event. I think I signed up the next day for classes at Northern Illinois University and never really looked back. At the time, NIU was the only undergraduate program in Illinois. That is now not the case anymore. Of course, we have a pretty large program in Champaign-Urbana, but still in terms of size, we're still the second largest program in the state undergraduate-wise. And we have about 10 or so graduate students in our research group now, two PhDs and about 8 master's students. A lot of my motivation for research, this goes way back to master's level work at Northern, is looking at this interannual variability and also just the longer term trends in billion-dollar losses associated with severe convective storms, which are shown here as the green bars on the histogram. And you can certainly see, especially in the last 10 to 15 years, that we're seeing more and more of these events on an annual basis. And the question really becomes is sort of what's driving this? Is this a climate signal, or is this sort of growing human footprint, right? Larger cities. And as we'll see, it's sort of a mix of both. But what's also very interesting, right, is this year-to-year fluctuation in the fact of basically weather and climate anomalies that are helping drive these sort of billion-dollar losses. Anytime one of these events happen, I think back to last year, the August 10th, 2020 derecho, you can almost guarantee that I'm going to have an email in my inbox from somebody in the Associated Press or some news outlet that's going to want to ask about whether or not this was, event was due to climate change. That's obviously a very flawed way to ask a question, because oftentimes you're coming at it the premise of not even understanding A, the event, or B, what you're blaming the event, what's driving the event, what you're sort of blaming this large scale climate anomaly or trend in climate for local scale. Of course, there's scale mismatch issues, there's temporal considerations to think about here, but we're still, as a science, right, very, very young in this, what is called attribution world, which is trying to play with toy models to try to understand individual events and how they fit in the larger probabilistic change of landscape of these events occurring. And anytime these events happen, we always wrestle with this issue. It's always in the forefront of the media, and it seems like we still have these, we're still having these scientific debates about really how big a role of anthropogenic climate change is having on modifying the probability of these, rather small events in terms of space and time. So my dissertation work tried to tackle that by using global climate models. And of course, you're already thinking global climate models, very coarse scale. We're talking maybe 1 degree horizontal grid spacing, right? Limited vertical resolution. How in the world are you going to study something like a tornado? And the answer there is we're not. We're using that GCM data to initialize, basically, you can think of it initializing regional weather prediction models. So initializing limited area models using the boundary conditions from the GCMs, initial and lateral boundary conditions, to then drive simulations at convective permitting resolution. So we really are trying to resolve supercell scale, storm scale convection when we're driving these GCMs. Another one of my research areas right now, and this is one that we have a current ongoing NSF grant for, is trying to understand what we call the intra-seasonal variability in severe convective storms. And here's a great example of this. This really, my wheels started turning on this after April of 2011. This inset here shows all of the local storm reports of tornadoes during April of 2011. And you can see how nicely that at least subjectively correlates with the number of hours from Reanalysis that experienced here a significant tornado parameter value greater than 1. So not surprising, right? The background environment, if it's conducive for tornadoes, is going to permit tornadic thunderstorms to at least, in some cases, develop in those associated environments. We know that severe convective storms are a function of their environment. And so showing it this way basically describes, right, okay, this was a very anomalous year centered on the Mississippi Valley, and we had a significant anomalous number of tornadoes in April 2011. Of course, this particular year drove a field campaign called Vortex Southeast. And in fact, there was congressional appropriation for a specific congressional appropriation for studies like Vortex Southeast. And the first year of Vortex Southeast, this is what happened, right? With any good field project, your first year, you have nothing in your domain, it seems like, from a severe convection perspective. So that begs the question, right? What drives in April 2011 versus in April 2016, where there's a significantly reduced number of STP hours and associated very few tornado reports in the same region? What makes an April an April an April, right? What makes a May a May a May? And we're interested in studying those leading modes of weather and climate variability that set up to perhaps favor or disfavor severe convective storm occurrence across the United States. So that'll be sort of one of the questions we'll discuss here today. If we have time at the end, we'll talk a little bit about the climate change impact and some ongoing work that we have that's funded through the National Science Foundation to track mesoscale convective systems and understanding how their track intensity, size, et cetera, may change in the future, which is vastly important for Midwest hydroclimate and agriculture. Nearly 90% of the precipitation in the warm season in the Midwest is due to mesoscale convective systems. So that's one thing that we're really interested in from a climate change perspective, are these larger scale convective structures and how they potentially will change in the future. A lot of my methodology for research, Angela mentioned Deputy Director of the CRCD, the Computing Center. So I do a lot of high performance computing. That's because these downscaling simulations require months worth of computational simulations, and that's running on dozens of nodes at once. Of course, you hear buzzwords like machine learning, statistics, neural networks. Those are becoming more, I guess, popular in my workflow as we're trying to extract information out of these climate simulations to make sense of them, sort of filtering out the signal from the noise, if you will. And I have a very soft spot for data visualization. Prior to coming to NIU, I was at the College of DuPage, where I focused on undergraduate teaching. But you're probably familiar with the weather.cod.edu, the WeatherCod site, where I helped develop the GOES 16 and 17 satellite pages, and also still have a hand in developing their models page. So if you've ever used the numerical weather prediction data from COD, I had a hand in that in the past. So I'm really interested in data visualization too. I still serve on some Unidata advisory panels that wrestle with some of those issues. So diving in here, I actually need to make sure that I may have to stop sharing my screen so that audio is going to come through. So let me stop share for just a minute. And when I go back to share, I need to share computer sound. There we go. So hopefully that didn't ruin your recording, Pete. But now this will share my audio. So I thought it would take a great place to start would be to start with history. So let's take a quick run in the past of discuss some historical tornado events and how we can look at those through a lens that can help us describe what's happening now, and then again, what's expected to happen across the tornado landscape in the future. So hopefully this will work. Hopefully you can hear this audio in your end.
The most devastating series of tornadoes in many decades rips through 6 Midwestern states. In the wake of the twisters, there are nearly 250 people dead, with damages mounting to the hundreds of millions of dollars. Iowa, Wisconsin, Arkansas, Indiana, Illinois, and Michigan were all hard hit by the deadly tornadoes as they slashed across the heart of the Midwest.
I actually did my senior capstone on that event. That was Palm Sunday, 1965. Those of you living in the Midwest at the time, if you were alive, was a very significant tornado event. And we can learn a lot from those sort of events, and especially the ones that cause injuries and fatalities going back to even 1900. Those are the ones that generally get logged in our database.
Hey, Victor.
Yeah.
We can hear the audio, but there's no video. Was there supposed to be video with that?
Yeah, there was. Shoot. So
I see your desktop.
Okay. Can you see my screen now or not?
I can see your desktop, but there's no video on it.
Okay.
Well, there's your PowerPoint.
Now you can see the slide. Well, anyway, it was a video back from, I think I just shared the wrong screen when I came back online. So my apologies. It was a video of the Palm Sunday 1965 tornadoes. So we'll have to catch up and show you that some other time. But these events in history generally don't get logged in the database unless they cause injuries and fatalities. In other words, a tornado in Kansas in 1940, 1950, right, didn't get logged unless it caused damage to a homestead or a farmstead. If you look at the number of significant tornadoes through time, you'll actually see no trend at all. EF1s, EF2s are greater. You can see we're sitting right at an average right about 200 a year for EF2 plus. These are what we consider significant tornadoes. And in general, we don't see trends in any really of the categories when it comes to tornadic environments in the black line, or even say EF1 or greater tornadoes. It's actually a very reliable record. Where the record's not so reliable are in wind and hail. You can see this exponential increase, especially starting in around 1980. This is really the beginning of things like Skywarn, of course, Doppler radar coming online with the modernization of the Weather Service in the early 90s, the advent of really technology, storm chasing. This is, we're capturing more reports than ever before. And so if you don't normalize for those sort of changes when you're looking at reports, it's easy to say that, this is, it must be climate change increasing hail occurrence. Well, Obviously, it's not. It's a function of just how poor the database was prior to 1995. And in fact, when you begin about 95, 96, when the modernization of the Weather Service was complete, these records become much more reliable in terms of not only their interannual variability, but their spatial occurrence and the way we capture them are all much more reliable. So you got to be careful sometimes when you look back in history at some of the events, because you're probably not capturing the full gamut of the distribution. What you can do instead of relying on reports, you can look at environments. So this is the idea of, let's say, a tornado watch day, right? The conditions are favorable for the development. Doesn't necessarily mean you're going to get one, but the conditions are favorable. And this is what we call the ingredients-based forecasting approach, right? If you want to bake an apple pie, you have to have a subset of ingredients. If you want to make a tornado, as I tell my students, you must have SLIM. You must have wind shear, right? You need lift, instability, and moisture for thunderstorms, but for organized convection, you have to add in vertical wind shear. Of course, with tornadoes, there's other ingredients. You want generally low, relatively low lifting condensation level heights. You want significant amounts of streamwise vorticity, et cetera. But in a basic climatic sense, you want 4 major ingredients in order to create an environment that's going to be conducive for a tornadic thunderstorm. And so the seminal paper that sort of looks at this from an environmental perspective is Brooks et al. 2003, where they show this deep layer wind shear on a log scale on the y-axis, and then instability, so measured by CAPE, on the x-axis log scale. They show that a majority of the events that are what we call significant severe, the ones that are most likely to cause great loss and property damage, are found when the product of CAPE and shear is high. And they created this nice discrimination line through statistics to basically, this is a classification problem, right? Where they show that if the product of CAPE and shear is greater than 20,000, that's basically unitless when you scale it, that the environment favors significant severe weather. So you basically want a significant amount of convective instability or very low static stability and a significant amount of vertical wind shear. Those are the types of environments that favor significant severe weather. Now that you have just the ingredients, you don't rely on reports or humans, you can go look at reanalysis data sets, right? And begin to pick out where those ingredients are most frequent. So we updated the Brooks et al. 2003 study to look at where globally we see favorable tornado environments from reanalysis, knowing that we're not going to get reports of tornadoes, right, in portions of the Pacific Ocean or the Atlantic Ocean, or even in portions of Australia where we just don't have a significant population to report any tornadoes to us. And of course, the reporting procedures by country and by continent vary widely. As some grad students in your program are already finding out, there's not a global repository for severe weather occurrence. Of course, if you're interested in severe convective storms, you're living on the right continent. North America, because of our unique geography and the steep, the continental divide to our west, creating elevated mixed layer air masses, the Mexican high plateau. It's really that continental tropical air mass in the spring advecting over the boundary layer moisture that creates steep lapse rates that you need for severe convection across most of North America. And you do find that type of environment in South America, right? With the Andes, the Relámpago project just finished up in Argentina, where they see there some of the world's largest mesoscale convective systems, and they do have environments favorable to large hail and significant tornadoes as well. It's just that instead of the Gulf of Mexico, you generally see transpiration of moisture from the Amazonian rainforest. Globally speaking, though, there's really no other, there are other hotspots. In fact, Bangladesh, Southeast Asia is one of the hotspots for global tornado activity, although it's very localized. South Africa and the eastern portion of Australia does see significant tornado events from time to time as well. But you can just see sort of how overwhelming the central plains are of the United States in terms of a tornadic frequency. And notice also, no surprise, but where you see the hotspots are in the mid-latitudes, right? You generally don't see tornadic environments favorable in the tropics or say north or south of 60 degrees latitude. When you zoom in, this was my master's work, pretty coarse resolution reanalysis here, but when you zoom in on the United States, you can see a little bit more of a picture of where quote unquote objective supercell alley would be defined if you allowed a computer to do it. So if you relied only on the environments, this is where reanalysis suggests the United States, where supercell alley would be. I notice I don't say tornado alley because this is just looking at the number of days per year supportive of supercell composite parameter. And you can see, no surprise here, it sort of extends through central Texas, up the I-35 corridor from Dallas-Fort Worth through Oklahoma City, and then up towards, say, Wichita and Topeka. Perhaps, 2.5 degrees either side of that line. But notice how that extends pretty far north. The frequency of supercell favorable days in southern Minnesota is actually very similar to deep layer boundary supercell days in portions of the West Texas or the East Texas Panhandle, which is not something I think a lot of people, conceptualize. They do think of this area out here as, supercell tornado country, and it is. It's just that it's really hard here to get the deeper boundary layer moisture that you need for significant tornadoes. Say when you get west of, say, the 100th meridian. So that was some of my master's level work. And of course, inside of that contour, we've had some pretty significant events. We have the May 20th, 2013, the El Reno F5. We have my favorite tornado video of all time. If you've never seen this before, I'm going to play it for you really quickly because this is by far and away, if you're interested in tornado history, this is the most remarkable tornado video of all time. And I want you to pay specific attention to the audio on this one.
Shit. Susan, get my pants.
So if you couldn't hear that audio, he says in the beginning of the video, he goes, shit. The tornado's not moving left or right. If it's just getting bigger, it's coming right at you. I think he finally realizes that about halfway through that video. You can go check it out on YouTube. And then he calls to his wife. He says, Susan, please get my pants. This guy is watching a significant tornado moving right at his farm with no pants on. So I found that to be a rather amazing video. And of course, you can get remarkable events outside of, the pinpoint contours here. This is one of the most famous tornado photographs of all time from the Palm Sunday 65 outbreak of twin EF4 tornadoes in northwestern Indiana. And again, an event that I studied quite heavily during my undergrad and grad school days, and is still one today that, if happened today, would probably be nearly a $10 billion event just because of the population density in some of these areas today. So I'm going to skip that because that's not as important as this one. This was a recent study that I did with Harold Brooks of the National Severe Storms Lab, where we tried to come up with one of these, again, going back to this idea of environments. Can we capture a reanalysis environmental metric that explains a significant amount of the variance in tornado frequency from year to year? So sort of looking at these interannual fluctuations. And it turns out that if you look at annual tornado counts, you can correlate them very well with what's called the accumulated significant tornado parameter. So what we do here is basically every day, if you're familiar with like ACE for hurricanes, it's kind of like a similar thing for severe weather. So we tally up all of the significant tornado parameter in the United States for the day, and we just accumulate that through the year to sort of get this, it's like accumulated rainfall, only we're looking at accumulated favorable tornado environments. And it explains a significant amount of the variance in year-to-year tornado activity. And so then we use that metric, the STP, to then look at spatially how things have changed across the United States from 1980 to present. And this is probably one of my most famous research productions. This got significant media attention. In fact, I'll tell you a story one day over a beer of why it was rejected in BAMS. But ultimately, it was good because it ended up being accepted in an open source Nature publication and got a lot more press, I think, than it would have in BAMS. But we were able to show that basically the trend in favorable tornado environments across the plains has maintained steady or actually decreased in portions of the plains over the last 40 years, while portions of the middle Mississippi Valley, Midwest, and Southeast have seen robust increases in the number of favorable tornado days in the last 40 years. And of course, this is not a shifting tornado alley. It was said, in the news, it was always coming up as this shift in tornado alley. It's not a shift. We still see the greatest number of tornadoes in the Great Plains every year. However, it's just that the trend there is downward, and it's upward in areas that have a very high vulnerability to tornado casualties. whether that's injury or fatality, because of the high number of mobile homes that we see in the southeastern United States, and the fact that these events are more often to occur in the early spring, in the overnight hours, associated with things like quasi-linear convective systems or embedded circulations. There's a whole host of reasons why we see more tornado fatalities here. But in the base premise, we just have more people living east of the Mississippi River with a higher population density. So there's really just more targets for these types of tornadoes to hit. So this, of course, got a lot of news. I was on the PR circuit for a while, but this is probably the coolest thing ever to come out of any of my research. Never in my wildest dreams did I believe that in the front page of the Omaha World Herald, the syndicated cartoonist Jeffrey Katerba would have drawn a cartoon about our research, saying that tornadoes are shifting to the east, and the parent tornadoes here are saying, I don't care what others are doing, we're staying put. So that is something that I have framed in my office, and if I ever get back in there due to COVID, we'll have to take it down because I miss looking at that on a daily basis. But sort of a pretty cool thing when you see your research catch fire and spread like that. It's a very humbling experience, and I think throws you full force into the wild world of research dissemination and media, which is a whole other beast that I don't even want to talk about right now. So if I had to summarize the past, apparently people in Nebraska film tornadoes without wearing pants. I had to throw that in there. We haven't seen a significant change in the annual frequency of SCS. In other words, if you look through time, the most reliable aspects of our records, we just don't see an indication that tornadoes are becoming more frequent. There are changes in the spatial frequency, and those changes certainly put more assets at risk. But the most notable aspect of the severe weather database that we have to date is this increase in standard deviation on any given year. So we see an increase in the interannual variability. There are some years that have very high tornado counts and some that have very, very low. And we see just the broadening of that distribution over the last 20 years and sort of a decrease of what's just average. We tend to be very, very high or very, very low, which if you put on your synoptic meteorology hat, right, that sort of suggests to you that during tornado season, we tend to be either locked in climate regimes, weather regimes that are either very favorable for severe convection or not so favorable. And we think that could be tied to jet structure dynamics, high amplitude blocking. There's a lot of potential reasons why that might be happening, but none of them are really well understood at this time and definitely warrant further research. So if we move towards the present here, again, we have kind of an idea of the scope of what's possible with tornadoes in terms of their spatiotemporal frequency, what to expect on any given year in terms of bounds, putting bounds on tornado wind speed and things like this. But I want to talk just briefly about current efforts in forecasting and where we are present, and really how far we've come in the last 30 years. Many of you that are interested in severe convective storms know about the Storm Prediction Center. They are the governmental agency that's tasked with providing outlooks for severe weather and tornadoes as many as 8 days in advance. And we're actually partnering with SPC and CPC to begin to investigate seasonal outlooks for severe weather. In other words, providing something like an 8 to 10 day forecast, a 14 to 16 day or 10 to 14 day forecast of what they do for their temperature and precipitation outlooks, but provide those for hazardous extreme weather, including severe convective storms. And of course, the SPC, if I had to pick one agency within NOAA, or one of the national centers, including the Hurricane Center, that just does a fantastic job, the SPC is constantly pushing barriers and pushing the envelope of what's possible in severe convective storm prediction. So they issue, right, the tornado watches. These forecasts, if you watch the 9 o'clock news at night, you see Doppler radar analysis and the meteorologist probably trained looking at dual pole fields and extrapolating out where this severe thunderstorm is going to be. It's remarkable how far we've come since the super outbreak number 1, which was April 3rd, 1974. If you think about the progress that's been made in the last 40 years in tornado prediction, it's rather remarkable. Now later, I'll argue that I think we've hit an asymptote, and it's going to be pretty hard to make significant strides forward without a very, very significant investment in observations. But It's a testament to technology, and you can see this bore out in basically technology and in awareness. The 1925, the March tri-state tornado of 1925 really was the end of an era in terms of tornado fatalities. Every year since then, you can see we've had this sort of decrease in the number of people being killed by tornadoes. This is a function of the advent of Doppler radar, awareness, sirens, outdoor warning capability, just our understanding of tornadoes, the environment that they form in. I mean, go back to World War I, you're thinking about, even as back far as the initial forecasts at Tinker Air Force Base in the 40s that were looking at the conditions favorable for tornado environments. So this is really a function of many things that have helped drive this number down. And of course, many of us argue that not only is this going to flatline, we're probably going to begin to see, either a flatline or an increase in the number of deaths per million people. And we'll get into why that is later. But we've been able to, this is a good thing for tornado scientists. We're able to drive that number down by an order of magnitude. But I don't think we're going to get much lower than that. What's remarkable is the skill increase in forecasting. And this is primarily due to understanding the conditions that are favorable for tornadoes, but obviously numerical weather prediction. So, there's a huge leap about 10 years ago when we got over that parameterization gray zone and we got into the convective permitting, right? 3 kilometer, 4 kilometer horizontal grid spacing. We could start to resolve the parent convective structures that were responsible for these sort of events. And here's an example of a Storm Prediction Center day 6 forecast in the green, then day 5 in the purple, 4, 3, 2, 1 in the eventual outlook and reports, right? This is the ability of numerical weather prediction to instill confidence in a forecaster that he or she can issue an outlook that many days in advance that is then going to verify both in space and time. And you can see the forecast here was quite good. And this, of course, is just one cherry-picked event. There are cases even on day 1 where we make very, very poor forecasts because the problem of the day, so to speak, is perhaps not being resolved properly by numerical weather prediction or whatever. But it's still a testament to how good and how far we've come with NWP. And so one of the questions that I asked as a researcher is, if we take our flagship weather model in the US, which is the GFS, how far in advance can we predict severe weather just using the environmental information? And furthermore, if you're looking at that skill, how does that skill vary as a function of time? And so we needed a way to address this. And the way to address this from a forecaster point of view is to issue a tornado outlook. And that's what SPC does. Here's an outlook for the 9th of April, 2015. You can see the forecasters here issue their outlooks in what are called probability contours. So on this particular day, there was a 10% probability of seeing a tornado within 25 miles of a point inside of that polygon that's shaded yellow. Well, you have a forecast and then you have an event. So here's the event. Here are the reports from that particular day. This is actually the day of the Fairdale tornado in Northern Illinois. That I helped survey, the EF4, and pretty good forecast. I don't know how you would grade that, but it would have to be subjective in nature. But you might look at this and go, that's a B minus. There's a lot of false alarm area, but it did capture the area perhaps of greatest spatial density. There's not an objective way, and so we need an objective way to grade these sort of forecasts. And so we did that by using Practically Perfect. This is a paper that will be out in the next issue of BAMS. So when you get BAMS in your inbox delivered to you digitally this month, we should be one of the papers in there. And we describe this Practically Perfect approach. But the idea here is basically to just spatially smooth the severe weather reports to something that matches what you would expect from an SPC forecast. So in other words, if you knew the outcome, then draw a perfect forecast. So it sort of looks like this. Let's say we have a tornado event. Here are the tornadoes for a particular day. We could then go back and match what a perfect outlook might look like if you knew what was going to happen in advance. So it's like having a priori knowledge of the event, and then you go back and apply this spatial Gaussian smoother to get something that would represent a Storm Prediction Center forecast. So that's the premise behind how we're going to grade our forecasts from numerical weather prediction. So in this study, the flagship weather model was the GFS Ensemble, right? We definitely want to take an ensemble approach so that we understand how this skill is functioning how skill is functioning versus probability of these environments occurring. And so then we can look at things like the Breyer skill score if we're looking at a probabilistic framework, in addition to a lot of the other metrics that we can, traditional skill score metrics that we can use. And we're looking at them in the context of climatologies. In other words, can we beat a climatology forecast? Our predictor is going to be every single member of the GFS ensemble. And we are going to predict the practically perfect slight risk events. We didn't do moderates or highs because your sample size gets too low, but we did look at this for both hail and tornado. So again, if you're just not familiar with the GFS ensemble, now it's been upgraded with the new FV3 dynamical core. So there are now 30 members plus one control member. But at the time this research was conducted, this was the old spectral version of the GFS. It had 6 hourly output to 384 hours, horizontal grid spacing of half a degree. And we trimmed to only look at the coverage of the United States where we have severe weather reports that are reliable. The true predictor from the GFS ensemble is going to be the environmental method. And I'm going to describe what that environment is in just a second. But similar to the outlook process, just like a forecaster looks at a map and says, these are where all the ingredients are intersecting for tornadoes, we're going to do that same sort of thing inside of the model framework. So here's the specific environmental metric that we're looking for. We're looking for the supercell composite parameter, and we're looking for it where the model also is producing convective precipitation in the following time step. In other words, there's a favorable environment, and then the model does release convection. We wouldn't want to look at this if there's no convection, right? There's perhaps a strong capping inversion, or for whatever reason, the environment just wasn't utilized, which does happen a lot when you're looking at favorable environments. So our predictor from the GFS is going to be this supercell composite parameter from every member. And the SCP is just a function of instability, low-level storm relative helicity, or at least storm relative helicity that's favorable for supercells, and deep layer vertical wind shear. We throw out the first 12 hours and the last 12 hours of every 0Z cycle, leaving us with 15 12Z to 12Z periods. These 12Z, 12Z periods, we then calculate the practically perfect for each 12Z to 12Z period, and voila, we have our predictor and our predictand. We can't do this on points, right? So that's the beauty of practically perfect. And I, again, would point you to the BAMS paper this coming month to use practically perfect instead of these point estimates of hazard occurrence, because they're more representative of the background spatial structure of the hazard and how it plays out. And it's directly relevant to Storm Prediction Center operations. So we looked at this for all of March through May of 2016 and 2017. So that gives us just under 4,000 forecasts. And here's an example of essentially how this works. We have knowledge of the event. We only care about the event where a particular threshold is met, in this case, the slight risk. And then we have a bunch of predictors from our GFS ensemble. We can look at lots of different various metrics here. You could look at the mean, the median, the max, the min, the standard deviation. Here, just an example, I'm showing you where the average value exceeds 2. And now, of course, if you're on a grid, you can calculate all of your typical verification statistics, your CSI, and a probabilistic framework. You can calculate the Breyer skill score, right? Where they overlap, you're hitting, where you're missing the target, where you're correct nulls, and so on and so forth. So can't look at accuracy here, right? Because you're going to have tons of correct nulls with extreme environments. But you want to really focus in on things like the critical success index, the success ratio. Basically look at performance diagrams that are telling you how reliable your forecast is relative to a known skill level, which in this case is climatology. So here's the results from that work. And the only panel that really matters here is panel C. We did this for tornado and hail, as I mentioned. Look at the drop off in Breyer skill score as a function of lead time, such that if you're using the GFS ensemble, right, which is our flagship ensemble in the United States, then you really have no business predicting severe weather over climatology, at least for tornadoes, past day 9. And for hail, you have really no business doing that. The skill is greater, right? It's increased. We have greater sample size, a little bit easier to predict environments that are favorable for hail versus tornadoes. But your skill approaches 0, which is telling you that you're not any more skillful than a climatology forecast at day 12. This, for those of you in the audience that teach numerical weather prediction or are savvy modelers, this shouldn't just be surprising to you at all. This is, Lorentzian chaos. We understand that initial condition problems show decay in skill with lead time, but now we at least know where the bar is set. This paper, if you want to take a look at it, is published in GRL back in 2019, but just shows a function of these skill scores by lead time using the environmental metric. Now, that might not be the best way to predict, but at least gives you a first order estimate of where the benchmark is, right? Where's the bar that you need to jump over? And you can see for tornadoes, if you're going to lift the bar at all, you're basically starting at a skill of around day 9 or so. So that transitions into what is becoming very, very difficult. And that is, what happens when you are no longer interested in an initial condition problem anymore, and you're not interested in a forced boundary problem like seasonal forecasts, and you're interested in this, what I kind of akin to the parameterization gray zone in numerical weather prediction, right? We have this gray zone right now in forecasting where we don't do anything, between say 2 weeks and 2 months. And this area called subseasonal variability is of utmost importance right now to NOAA. There are several task forces in not only NOAA, but in private sector endeavors that are trying to increase the skill of subseasonal forecasts. You just saw this element that I showed you with numerical weather prediction, this decay in skill over weeks 1 and into the early portion of week 2. But there is still some skill around day 2 that we think we can harness to kind of create this bridge that's between the initial condition and the forced boundary problem. And it's going to require us to couple dynamical models with statistical analog models. So really coupling dynamical models with machine learning and artificial intelligence to extract out signal from these from the noise, especially when you get out towards the end of the week 2 era, or the week 2 portion of the prediction, and really leverage whatever skill is left to be able to make these successful subseasonal forecasts, which I will show you it's not always possible to make these successful forecasts. These are what we call forecasts of opportunity in many ways. And I'll mention that here in just a little bit. So if you look at this area, this orange area of research, as it relates to tornadoes, we've put out a lot of papers examining various modes of climate variability that load the dice to either enhance tornado environments across the United States in the spring or mitigate against them. And the leading mode of variability in the Northern Hemisphere is the Madden-Julian oscillation. So it's basically tropical convection in the Indian Ocean across the maritime continent and then eventually into the Western Hemisphere. That drives a majority of the variability that you see in the Northern Hemisphere. And that's just full stop. That's basically all modes of extreme weather. If you're looking at the subseasonal framework, and we'll talk a little bit more about the MJO in just a second, but another one is the result of MJO on the global circulation. And that's Earth relative atmospheric angular momentum. And I do want to mention that a little bit later because we have been able to link global changes in atmospheric angular momentum to favorable synoptic regimes that produce tornadoes and also ones that mitigate severe weather occurrence. So, in summary here, MJO convection, we know, plays a significant role in these budgets and is something that we have to be cognizant of, especially in the early spring. Once you get to the summer, predictability really drops, especially in June and July. A lot of the forcing for ascent is mesoscale driven, and the synoptic sort of fades away once you get deeper into the warm season, and we just don't have that subseasonal skill that we have in the early spring. If you're not familiar with the MJO, just a very quick primer. The MJO is described in one of 8 phases, and it's just where a majority of the convection across the equatorial Indian Ocean and then out towards the date line, wherever it's centered, wherever that convection is centered, and the strength of that convection determines where you're at in what we call the MJO phase space. The MJO does propagate eastward, and so you'll typically see these events. They're actually circumglobal, but you'll see these events typically come off, flare up in convection over the Indian Ocean, which then propagates through phases 2, 3, and 4 across the maritime continent, and then eventually out towards the international dateline. And associated with that, right, are changes in outgoing long wave radiation, precipitation anomalies, subsidence versus ascent, and so on and so forth. So that's just, if you're not familiar with MJO, that's basically what we're looking at here. And you can take these numbers 1 through 8 and the strength of the convection to then map out where the MJO is and how strong it is using what's called a Wheeler and Hendon phase space diagram. So in this particular example, the convection is between phases 2 and 3. And so on this diagram, we would say that, the MJO would be down here near the Indian Ocean. You can see the movement of the MJO is typically counterclockwise. And the farther you are away from the origin, basically just the stronger the leading modes of explanatory power are. So in this case, RMM 1 and 2, which are looking at 850 wind anomalies and outgoing long wave radiation. Those are sort of the two leading EOFs of the MJO. There are other ways to look at it, velocity potential. Greg Tripoli and I were actually talking today about using things like potential vorticity and things to track these sort of changes in the global scale budget. But the MJO, this is very specific to the MJO and is used widely by folks like the CPC or long range, subseasonal range energy forecasters that are trying to understand the potential for variability in the weather and climate regime using MJO. So to take the MJO a step further, what you can instead do is look at the resultant impacts of MJO on jet structure. And this is where a lot of my early research started, looking at Earth atmospheric angular momentum, which I promised myself I wasn't going to show any equations today, but it's the triple integral of UDP. So we're really just looking at the zonal wind integrated at every latitude, longitude, and vertical level. And when you do that, you get these nice, this is basically a zonal profile of atmospheric angular momentum. And so if you can think about what happens, if we have tropical convection, and the convection obviously is displaced vertically at the tropopause, then it basically acquires, as a part of the Hadley circulation, when it acquires its northward component of velocity towards the axes of rotation on Earth, it must acquire some sort of zonal component, right, through conservation of momentum. And so it's the idea of the Coriolis force. It acquires an eastward component to its velocity. And so in the tropics, we typically have a source of atmospheric angular momentum with the trade wind easterlies. In the mid-latitudes, we have a sink. And the beautiful aspect of atmospheric angular momentum is that it must be conserved. So when you have changes in the budget, they're pretty predictable 40 to 60-day cycles that align well with the MJO, although not perfectly. They align well to describe this sort of variability. So instead of looking at the source point of MJO, we're looking at the resultant structure of atmospheric angular momentum of the tropical convection on the global circulation. So it's a nice way to capture everything that's going on from this tropical convection and the influence that it plays on the global budget. And you can just imagine, right? Imagine a weather regime that's high angular momentum. You have, zonally oriented jets, very, low amplitude waves versus a very low atmospheric angular momentum pattern, which is highly meridional, high wave number, lots of blocking. And you can imagine that low atmospheric angular momentum would be more conducive to sort of patterns that would be favorable to, say, cyclogenesis and extreme weather. And that's certainly the case. So this particular study, these two studies actually, I got this idea watching the World Series one year. I can't remember, it was like the 2015 World Series. And Fox was showing the heat zones, right, of batters. Like, don't throw this batter low and inside because they're going to crush home runs, right? Their StatCast analytics were like, I'm like, I wonder if we could do that for MJO. Let's show where tornado outbreaks happen in this sort of phase space. We're in this strike zone. And it turns out that If you really want significant tornado events, EF2 or greater, and more than 10 happening on one day, then you want low atmospheric angular momentum and decreasing atmospheric angular momentum time tendency. So the first derivative is on the x-axis, and total atmospheric angular momentum in terms of standardized anomaly is on the y. So high AAM is in basically the top portion of this panel, and low AAM would be in the bottom portion. And we're in basically, if you're in Cartesian coordinate 3 here, quadrant 3, that's low angular momentum and also decreasing time tendency. So it's basically breakdowns of the jet structure in the Northern Hemisphere. So from a subseasonal perspective, like sort of what's driving this, what do you look for? You basically look for an increase in the Indian Ocean convection associated with the MJO. Once you see that, that's a very good precursor that the jet structure and AAM are going to begin to build, right? That convection is going to begin to add atmospheric angular momentum to the global budget. And across the United States, while that's happening for the first week or so, F2s across the CONUS are about 8 times less likely. This is obviously a textbook progression, but I think you get the idea here. By week 2, you're still in a very high atmospheric angular momentum state. In fact, this was just happening, folks. Very, very quiet across the CONUS when we had that big Arctic spill into the southern tier of the United States. This has basically been the last 14 days. We've been going through this right now. And I will argue in this talk that in the next 2 weeks, we're going to be progressing towards a pattern that's going to be very favorable for severe weather, again, across the southern Great Plains and southeastern United States, as we are currently making one of these subseasonal orbits right now. And then again, in a textbook way, maybe about a month after you started that process, an F2 tornado across the CONUS is about 15 times more likely by the time you've made this full circuit and you're back to removing AAM out of the budget in a fairly meridional type of pattern. So we put this to the test in May of 2019. We wrote a paper and published it in GRL, but this was basically a case study looking at an event where we were able to predict increase in tornado environments across the United States about 4 weeks in advance. If you're not familiar with May of 2019, this was a highly anomalous year. We haven't seen anything like it from a severe weather perspective since May of 2003, the infamous 10 days in May. Unfortunately, we had 7 fatalities during this 2-week period, 17 to 29 May. And the number of tornadoes, 374 of them, is about 3 times the number that you would usually expect during that 2-week period in May. So our paper analyzes from start to finish sort of how we were able to assess this and predict this happening in real time. These are the OLR anomalies starting 4 weeks prior to, let's call it 4 weeks prior to mayhem, right? Those Allstate commercials. Are you in good hands, mayhem? So 4 weeks prior to mayhem, we saw a significant burst in convective activity over the Indian Ocean associated with an MJO that was starting to flare up. And this was happening, this is what it looks like on the MJO phase space diagram. So this is basically a centered 7-day period on that starting 4 weeks prior to mayhem. I'm going to periodically show this chart on the right. The number of tornadoes in the United States are shown by these gray circles every day. So you can see not much activity here happening in late April. But we saw this happening in real time, this flare up, and we were thinking, all right, we've seen this before. You know, the atmosphere, of course, can certainly burn you. Past performance does not guarantee future results, of course, but this physical linkage of the MJO convection to changes in the budget of AAM to eventually getting downstream and influencing the CONUS synoptic pattern is something that we were watching very, very closely. And so on our website, which I'll show later, we were discussing this event happening. And 3 weeks prior to mayhem, the MJO convection continued to propagate across the maritime continent, now centered basically right over the center portion of the maritime continent. And we actually even started to see what's very classic in some of these MJO events are the convection begin to move off of the equatorial 5 north, or right off the equator towards 5 north, 5 south. And that started happening about 3 weeks prior to the event. Here's where we are that 3-week period in MJO phase space. So we did have one day in there that had about 50 tornadoes. That was pretty notable. But the budget of AAM, right, was greatly being increased during this phase 3, 4, 5 period. 2 weeks prior to mayhem, the MJO continued to shift out towards the dateline. We're just west of the dateline at this point. The center of the convection is just at about 160 east, and the MJO continued to propagate, no surprise. Still pretty quiet in terms of US severe weather activity, averaging maybe 10, 15 events through that period. 1 week prior to mayhem, the MJO is way out all the way now towards the dateline, and this is basically the end of the quote unquote classic MJO event. And this is really where now, as a forecaster, you're already seeing this at this point, probably in the long range models, deep troughing beginning to set up in the Western United States. It's really, as you'll see in the jet structure, I'll show you in a minute, an extension and retrogression of the jet structure. But here's your continuation through phase space. And remember, right? Remember where you want to be. You want to be, if you want to hit a home run, if you want a tornado outbreak, you want to be down here in this 812 area. Really, anywhere over here is good for if you like tornadoes in the United States. And so you can see that's where we're coming, right, with this subseasonal signal here. So week 1 of the event, and you can see that now the number of tornadoes popping up. This is the first week of the event. We were averaging about 30 tornadoes across the United States. And then the second week of the event, no real OLR anomalies to note, although there was an event that was getting going again, just beginning to start. But at that point, the jet had already done its damage. It was basically a stationary long wave trough over the Western United States that produced southwest flow over the United States, southern tier of the United States in several days with favorable conditions for severe weather activity. So if you look at that period in isolation, this is from the GRL paper, this significant period here shown in MJO phase space sort of happened during what we call these 812 transitions of MJO phase space. And in terms of atmospheric angular momentum, these are periods where we have basically big extensions of the jet across the North Pacific. They become very elongated, zonally oriented, very high AAM, and they become unstable. And eventually the pattern sort of beta effect. We have this huge retrogression in the Northern Hemispheric wave pattern, and we get stationary long wave troughs and wave breaking to set up. And that's exactly what we got during this 812 transition. I promised the
Hi, Victor, may I interject here just for a second? This is Angela.
Yeah.
I just wanted to give you a heads up that we're at the end of our usual seminar time period. And I just wanted to give you a heads up if you wanted to allow for a few minutes for questions. People may have to sign off now, and I just wanted to give you a heads up.
I'm so sorry. I totally lost track of time.
No, there's a lot of great stuff here. I just wanted you to know. Yeah.
Very, 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 very important. And certainly if you have to go, sign off and sayonara. I will maybe break for a minute of questions or something. And then I would, for those of you who do want to stay in the line, I know I would like to show you some of the future simulations too with the climate stuff. So yeah, if there are any burning questions, maybe you can unmute yourself or type them in the chat. Would that be the best way?
Yeah, I think that would be great. Let's just give anyone a chance who may have to sign off here a minute or two to ask their questions, if you're okay with that. You can either raise your hand or put them in the chat, please. And I'm watching both.
Okay, awesome. So while we're waiting for that, I can kind of show this progression. So this is the jet.
That sounds great, yeah.
Yeah, this is the jet structure across. You can see this zonally oriented extension of the jet and then the breakdown. So this is basically week 1 of mayhem and week 2 of mayhem, where you basically set up, right, this stationary southwest flow over the plains. You get poleward moisture flux. I mean, very sort of classic, right? Severe weather regimes there. So let's see, just taking a look, we have chat. Okay, I think we're okay. So yeah, if you have to sign off, faculty, staff, grad students, just go for it. And if it's just me and Pete left with him recording, you'll probably be okay with that. So
we do have one question actually right now.
Awesome.
Yeah, go ahead, John.
Yeah.
John,
Sorry.
go ahead.
Yeah, John Martin here, Victor. Sorry I didn't get to meet with you today, and this is really interesting, and I'm not signing off. I just wanted to ask a question. Okay. What does the, do you have cross sections through the jet between week 1 and week 2 of the event?
Good question. We do not. I have investigated, I don't have them here to show you. I have investigated them. The vertical structure is interesting. It's like there's not, if you look latitudinally, this momentum is centered, right, much further north in this particular event. than you would generally see in like a, a subtropical slash polar, combination or something, or juxtaposition of the jets. That's not what you see.
Okay.
This is just an extended northward anomaly that's coming off east of the Tibetan Plateau. So we think that there is regional frictional torque that's happening with some of these events as the momentum gets added to the Northern Hemisphere budget, if that makes sense. But we do need to analyze more of the cross sections to see the changes in the dynamic tropopause and that sort of thing. I haven't looked enough into that to be able to sort of give you a good answer.
And one follow-up, thanks for that answer. And one follow-up would be, what about the cape on the equatorward side of the jet axis? Does that change dramatically between event minus 1 week and event week? Because one of the things we've noticed when we see these superposed jets make their way into the west coast of the U.S. is that you end up with positive cape from about 200 millibars up to 100 sometimes. That's not usually there. And so you get this extra oomph for whatever it is that develops downstream of upper waves. I don't know if that's systematic or if that's just, occasionally associated with cases.
I can say that was the case for this event. I don't know how common that is in terms of these forecasts, what I call kind of forecasts of opportunity or subseasonal cycles. Yeah. That sounds like a great project.
Yeah. Okay.
To try to understand.
Talk about it another time then. Thank you for your answers. Yeah, that's great.
Yeah, absolutely. Maria?
Yeah, we got a question from Maria.
Okay.
Hi, yeah. I had a question going off of something you mentioned earlier in your presentation where you said that you expected the amount of tornado deaths to either like plateau or increase. I just was curious what the reasoning was for that.
Unfortunately, I am trying to cram about 8 presentations into one, and so it's coming up later. In regards to trying to tie this all off with climate change. When we get past the subseasonal, I'm talking, I promise you, I don't have too much left. I have the future left, which is the climate change stuff. But it comes down to human exposure and vulnerability and the increasing human footprint. So that's, if you have to sign off now, that's definitely the answer as to why we're expecting to see a plateaued number of fatalities from tornadoes.
Thank you.
Yep.
And yeah, we'll let Steph ask her question too in case she has to take off. Thanks, Victor.
Yes, please. No, I apologize for being long-winded here. I spent way too much time in the background. So
go ahead, Steph.
Hey, Victor, this is really interesting. With regards to the MJO stuff, which is really interesting, I work with MJO teleconnections, so that's particularly interesting to me. Have you considered looking at lagged relationships? So the MJO, the MJO event that you showed tended to be strong for the entire event, from MJO phase 1 all the way around, tended to be pretty strong. But oftentimes the MJO is more episodic, where it'll strengthen and weaken as it propagates eastward, and it takes a certain amount of time for MJO Rossby waves to reach the mid latitudes. So I'm wondering if you've considered, and maybe you have, and you only showed parts of this, but to looking at lagged relationships, so that you are kind of attributing the MJO phase that was strong to the response over the mid latitudes in cases where the MJO event weakens somewhere within its cycle.
Great question. We looked at that in Barrett and Gensini 2015, one of our hail MJO papers, but you're right. It actually varies seasonally as well too, right? Because the wave propagation is different depending on the time of the year in terms of its phase speed. Yeah, those are all great questions. In fact, I have an NSF grant right now that one of the objectives is looking at lag lead relationships and better understanding what phase in, ENSO plays a significant role here that I didn't mention, but when you're looking at the MJO, you also need to kind of filter out for just lower base state frequency like ENSO. And so we tend to use like the PenTAD data or filtered MJO velocity potential to try to be able to look at this in more detail. The short of it right now is that I don't have a good answer for you in terms of the results from the lag lead relationship, although that is something we are absolutely considering and looking at.
Thanks. And I'll just quickly add, I wouldn't discount ENSO too much because ENSO will shift the MJO teleconnections and seasonally dependent, of course, since ENSO tends to be stronger in the winter. But it will shift the teleconnections and sometimes will act constructively or destructively with the MJO teleconnection. So you could get, in some cases, an enhanced signal, and in other cases, a lot of cancellation between those teleconnections, so that you're kind of getting rid of a lot of your forecasting ability, depending on what ENSO is doing. So there could be a lot of really interesting things that could be done with also considering ENSO.
You're absolutely right. Yep. And we're looking at that as well too. One of the things though is just to try to remove that base state signal to see how important the MJO is from a theoretical perspective framework first, but you're exactly right. It certainly can help load the dice in terms of constructive interference or mitigate against, a subseasonal cycle if you're not in a proper configuration of a base state. You're exactly correct. So
thank you so much. Yeah, it's really interesting.
Yeah. Okay, so I'm going to move on. I'm going to skip past this, and I'll just say that even with the best forecasts in the world, right, we're still going to have these events. And this was part of the question that was being asked before is, why do I think that these events are going to become more common? Part of this is the increasing, right, urban footprint. And I have some awesome results here at the very end that I'll show you for Wisconsin. The expanding bullseye effect in Wisconsin is probably more remarkable than you would think. But this is basically taking a hypothetical historical tornado scenario and moving it over various land uses at differing times. This work is done by a colleague of mine, Stephen Strader, and an office colleague next door to me, Walker Ashley at Northern, who's really looking at not necessarily the change in the risk, which I'll show you from climate modeling, but looking at the change in the vulnerability. And so this has nothing to do with climate change, but just to show you that we're going to have more of these disasters into the future with the same hypothetical event, just because it's going to impact more people. Madison, Wisconsin is actually a really great example of this. All right, well, we're going to skip past this just in the interest of time, but I love to do this with my talks. But I'm going to skip towards the present. Our forecasts are getting better for severe convective storms. I do say that I think we've had a critical key. Jumping over the convective parameterization gray zone to convective permitting or convective allowing was a huge stride forward for NWP. But I think we're at the point now where we're going to have a hard time getting much better unless we really invest in observations. And it's probably going to come from a more robust network of low-level Doppler radars. So C-bands that can be, really disseminated over a really large network to get understanding of the low-level wind field and being able to assimilate that sort of data into our models. We know how important radar assimilation is for day one convective scale forecasts like the high-resolution rapid refresh, the HER model. And so I'm above the camp right now where I'm just not sure how things like Warn on Forecast or some of these initiatives that are moving forward are really going to be able to make strides like we have in the last 10 years with CAMs, convective allowing models, if we don't have good observations. You can run the hell out of ensembles at convective permitting resolution and waste a bunch of computational resources, but without proper observations, they're going to be under dispersed. And I think we're going to have a pretty hard time getting past that asymptote unless we have better observations. So briefly, I only have like 4 or 5 slides here, but I just want to briefly talk about the climate angle, climate change in tornadoes for the future. This is some work I did for my dissertation, has been published on by others as well. This is work from Diffenbaugh et al. And PNAS showing the convective environments, the frequency change by the end of century. And you can see there's on average, if you look at your ensemble members of your GCMs, this is only looking at environments here. So we're not resolving any convection in the models, just looking at those supportive environments. We see a huge increase in March, April, May. Most of that increase is in March, but by the end of the century, about an increase of 42 days that would be supportive of severe convective storms. And you can see pretty robust statistical, obviously you have some field significance issues here, but a pretty robust, just across most of the convective climatology in the United States and even into Canada, an increase for the number of days supportive. And most of that is driven by low-level thermal energy. So basically increases in low-level theta E begin to outweigh, 700 millibar temperatures and associated convective inhibition. There's also an argument that, if we decrease the equator to polar temperature gradient, that should weaken the thermal wind. We'd have less days with vertical wind shear. But if you look at the number of days with instability in vertical wind shear in the models, basically your instability comes sooner in February and March when you still have a lot of vertical wind shear. And so the number of days on aggregate certainly increases. This is not enough though for severe storms, right? We can't look at just the models. We have to pass that data that's relatively coarse into something like WRF. And so this was a lot of my dissertation research to do simulations like this. These are basically decadal simulations that use GCM data to then drive things like WRF. And what you're seeing on the left is just downscaled composite radar reflectivity, where we then use machine learning to track these features and extract what are kind of synthetic perils, synthetic tornadoes, synthetic hailstorms, wherever we have rotating object. On the right here, we have lifted index. So blue is very stable air. Red air would be, relatively low static stability. And we run these simulations and we see things that are, very consistent in the climate models with what we'd expect. We see large extratropical cyclones as we get to May. We see the diurnal-driven climatology of convection on the plains. We see the sloshing of the dry line on some of these years in these simulations. These are fantastic, but unfortunately, they're so computationally expensive that it's really hard. Like, a decade worth of simulations takes about a year to finish. So, it's not a real, you can't really do ensembles with this sort of work right now. It's pretty challenging. But what it does allow for us, right, we're not interested in specific locations. We're interested in what happens on the aggregate sense when we go to things like RCP 4.5 or 8.5, as we begin dialing up, right, the greenhouse gas composition. Right? How does the convective scale respond to those sort of changes in the atmospheric composition and structure? And the answer to that is, at least from a preliminary sense, this is an aggregate, this is total number of severe weather synthetic reports. So this is model only, history in the black and future in the red. And what you see is not only do you see an average increase in severe weather from, again, this is deterministic. So this is just one GCM, RCM solution, but we have more years on the higher end. And we actually have two of the lowest years ever in the future as well, too, sort of telling you that we're already kind of seeing some of this. I mentioned this, right? Increase in the standard deviation, an increase in the variability from year to year. We have some years that are really high end and some years that are really low end. So we haven't been able to dig in yet and look at, all right, what's the mean 500 millibar composite analysis look like for these events? We haven't been able to do any of that. We're just looking at the storm scale, sort of some of the eye candy stuff. But some of the greatest increases that we found were actually aggregated in sort of this area where we're already kind of seeing a spatial shift, an increase in the number of severe weather environments in portions of the Mid-South. So we have some NSF money right now. We're running these simulations. This is kind of what it looks like. We have 15-minute output right now. We're trying to recreate history first. So we run these simulations, we compare them to reanalysis and observations, make sure that the climatologies look right. Then we apply these deltas, 4.5, 8.5, 6.5, and we try to get an understanding at the storm scale, and again, in an aggregate response, what this looks like. This is just an example of one of the downscaled simulations that we're running right now out on Cheyenne, and we should have those results, should be publishing, I hope, on those results in the next month or two. So, and finally, whew, you're like, God damn, he's finally done. Finally, this is my final slide. I threw this together for you just to show you the changing landscape, expected landscape of Wisconsin. This is basically change in land use land cover from 1950 all the way up through the SRES A2 scenario of 2100. So this is, we feel really confident about these land use changes unless something drastic happens, pandemics, 2008 housing crisis or whatever. But look at the area in and around Madison in terms of the growth, right? You think about this expanding footprint. Madison has a relatively high tornado climatology. I mean, it shares a tornado climatology with a place like Milwaukee or Rockford or even Chicago. And as the footprint continues to grow, of course, what you can do is simulate potential disaster in a place like Madison. We did this for DeKalb, we've done this for Chicago, but what you do is basically take a historical tornado track like Rochelle Fairdale, and you do a Monte Carlo simulation. You simulate thousands of times, and then you basically just capture what's the most impactful event, okay? In Chicago, the most impactful event is one that basically goes through southern DuPage County through northern Cook. No surprise. It's basically Plainfield, but instead of instead of Plainfield and northwest flow, take Plainfield and kind of have southwest flow. If you get that, that's a $10 billion plus tornado event just by itself. But when you look at the landscape of tornado events and you run these Monte Carlo simulations for Wisconsin, which is what I've done for you guys here, look at how this changes from 1950 to 2000. These are just POE curves, so probability of exceedance of the number of homes impacted by one single average tornado. Look at how that curve shifts by the time you get to 2050 and 2100, where the average probability of exceedance of hitting 1,000 homes was about the same average probability of exceedance in 1950 of hitting, 100 homes. So this is the idea of the expanding bullseye effect. And, certainly there's going to be spatial shifts and changes with climate. We're still trying to figure out exactly what those are, but we will continue to wrestle with these events, these tornado disasters, just because of the expanding sort of bullseye effect that we will continue to see. And so the future in terms of SCS impacts and disasters, that chart that I showed at the very beginning, these number of $10 billion disasters, we're seeing this with hail. We're seeing this with, we just saw this with the derecho. The derecho of last year is going to end up being tens of billions of dollars, not only in agricultural loss, but property damage and loss. And this number is not going away. And the insurance industry and reinsurance industry is very well aware that we get these billion-dollar losses. I mean, hail last year in the United States caused $10 billion in loss, and it's basically an annual $10 billion loss for the insurance sector. And certainly they're asking questions about climate change, subseasonal. When can we expect these sort of things to happen? And so it's very relevant to them, of course. And that was a ton of information. I feel like sometimes and Angela, you can probably relate to this as an early career professor. You feel like you have your tentacles in about 10,000 projects and you're trying to figure out where to put your time and effort. But that's just some of the stuff we're working on down here in DeKalb. And we would certainly be interested in hosting, some of your faculty or staff down at campus. We're only an hour and a half away. So I really wish, I certainly wish I was there and can go out for a beverage with all of you and talk more. But we've got some exciting things going on down here. I know your program is very well respected. We love what you guys have been doing in Madison for a long time. And we should definitely collaborate more because we're very close. So
yeah, thanks, Victor. I really agree. There's so many opportunities here with all the different expertise in this department, and just thanks for sharing such a broad perspective. In interest of time, I'll take another question or two, but of course, please follow up afterwards. I'm sure you're welcome to questions afterwards by email as well. Do we have any final?
I have a question.
Yeah, Greg.
Yeah, I think your talk was amazing. I think very, very good. One of the things I wanted to point out is a couple of years ago, we wrote a paper on outbreaks. I don't know if you've seen it in natural hazards, but what we did is we compared the last 20 major tornado outbreaks where you have multiple tornadoes climatologically to the existence of jet streams and subtropical jets. And what we found, interestingly, was 100% of the outbreaks are associated with a subtropical jet to the north of the storm, meaning that the storm was in a region of low angular momentum, as possibly you're suggesting, but also a region of low potential vorticity and low inertial stability at the outflow level. And so we look at it from a different point of view. I don't know if you've ever thought of this, but the inertial stability at the outflow level determines the amount of resistance to outflow. And when you have multiple storms in an outbreak, their aggregate outflow becomes very large, and there's a lot of resistance to having multiple storm. One tends to suppress the other. But in these instances where you have high amplitude of troughs and the ridge pushes to the north with the subtropical jet to the north, that's when you have the least resistance to pushing outflow and you can get multiple storms. Have you ever thought of that?
I'm thinking of it more now. I know we cited that paper in that monthly weather review because I had come across that. I honestly haven't thought about that, to be very frank with you. I think it certainly warrants investigation.
Yeah, we've been watching it, and we noticed that a lot of times when the SPC makes errors, they're not looking at that inertial frequency, the inertial stability. And we look at it, well, this is really high. It's not going to happen. They're just not going to happen. And as we expect, they blow the forecast. So we're just kind of watching that in a anecdotal way. But it seems to work.
Do you have any sense of the frequency of those events to understand, is there a null, is there a false alarm factor, or is it, purely in 100? I mean, how common is that? And then to not get an outbreak?
I think they tend to blow it like this, not all the time, but maybe say 1 out of every 5 times or something like that to blow the forecast, because they're not looking at that inertial frequency, and storms are going to snuff each other out. They think they're going to get a whole 20 storms all over the place. Instead, they get 1.
Yeah.
And I think this is a big factor, but it's a different way of looking at the same thing that you said, I think.
Well, thank you, Greg. I will dig into that more.
Okay.
Yep.
Liz, I see your hand up.
Sure, I'll ask a quick question. So cool stuff. I'm interested more in the future projections and how these kind of environments will change in the future. And I went to this talk last week, which basically showed that one of our standard metrics for Atlantic sea surface temperature variability breaks down after about 2040. The simple linear methods just don't explain what you think it's going to explain in the future. And I'm wondering, for these kind of metrics you're using for severe convective activity, how do you think these metrics hold up in the future? I mean, this is a very nonlinear process. Yeah. So is, CAPE and shear, when we get pushed into these totally new environments, still mean the same thing for tornadoes that it does today, or hail for that matter? How confident are you this metric will hold up?
It's a fantastic question. It is something that delta study, we call these delta studies, right, in regimes, that you always have to wrestle with, is the idea of, your assumption here is that the physics that produce the hazard now are the physics that are going to produce the hazard in the future. And so that, I think, is an okay assumption. But when you look at background convective environments, you're exactly right. If you shift the CAPE and shear space, for example, how maybe it becomes less efficient in the future. I think what has been shown, though, there has been a lot of work that has done theoretical, changing in theory, changing vertical wind shear, changing CAPE, not only at the storm scale. I mean, Jeff Trapp has done a lot of this work with CM1 and storm scale models to show, in a future, if you take this climate delta and perturb the signal of the vertical profile, how the storm scale responds. And it responds actually in a pretty predictable manner with what we understand about storm scale physics. Your comment about sea surface temperatures are well taken. Thankfully, we don't have to deal with much of the GCMs obviously rely on sea surface temperature, which then of course feeds back into the global circulation. So we are at the mercy of the skill of GCMs, of course, because any biases in those are going to get passed down, right, to your dynamically downscaled simulations. I think our biggest limitation right now is that we're just not able to run ensemble simulations here. We have no idea of the variability between GCM, RCM combination, how important is microphysics in all of this. We generally try to remove, we remove the convective parameterization scheme, but we still have boundary layer schemes, right? We still are at the mercy of general convective permitting. And of course, we're not at large eddy simulation or anything like that. So,
really, land models
or land,
and
right?
GCMs do a horrible job, and that's going to set what kind of profile you have up if just your soil moisture is totally off.
Of course, yeah. What we're kind of hanging our hat on right now is these RCMs, our regional climate models that are simulating at convective permitting resolutions, can adequately represent extremes in history. And so at least, and those GCMs, right, they're not reanalysis. I mean, these are free running GCMs. And so if we can create with these RCMs climatologies that look reasonable, then really what we're most interested in are the deltas between those two. So our paper that we published in Nature Climate Change about snowstorms, and that's all that was just applying a perturbation, a delta, using the NCAR simulations. That particular study was not even using GCM data. We were just using what's called the pseudo global warming approach, where you apply a delta to the reanalysis and then try to understand how your base state fields change. Those are all questions that we have to wrestle with when we're doing any sort of climate change extreme analysis work. So yeah, points very well taken there.
I have to jump off. So if anyone else wants to keep the discussion going, great. I just wanted to say thanks again, Victor, and I'll follow up with you for sure. And
Yes.
thanks for
looking
so much
forward to
interesting
covering.
material.
Yep. Yep.
All right, I'm going to take off. Anyone else is welcome to stay, of course. Bye-bye.
Yeah. If there are any other questions, I'd be happy. Otherwise, I'm sure you probably all have Zoom fatigue after that. Crazy. You can tell I'm a teacher that runs overtime, right? And the students are like, on my reviews, does not keep time, right? Hey, but sometimes you get, right, you can tell when you're passionate about talking about something. So
I have a quick question for you.
yeah, Kelton, go ahead.
Can you describe, because I know I've seen your TAP stuff that kind of goes from the Earth angular momentum anomalies to like regional gridded forecast areas. How do you go from the MJO diagram phase space of going like, okay, we're heading into a favorable pattern, to the more regional approach with the forecasting? Is that more subjective, or is there like a pipeline that goes from one to the other?
The pipeline there are using the leading modes of variability. So MJO, phase space. And what you can do is just use multivariate regression. I mean, machine learning is perfect with this because you can basically classify SOMs. So just say that, you say you have a 5-node SOM, and node 1 is a trough in the west. And so when you're moving across, you just classify that. That's then correlated to the practically perfect. So you're basically using the SOM to create a gridded practically perfect.
Okay, so you can just like statistically relate, like observe patterns together, and then whenever you reach that,
kind of just a fancy way of using an analog method. So there, of course, you're constrained to the observable period of history. So when you get these anomalous events that are outside of anything that you observed, you obviously break down there. But using that with linear inverse models is really skillful out to weeks 3 and 4 when you have these predictable regimes. They're not always there. Yeah. And that's why we try to call these, windows of skillful opportunity, or windows or forecasts of opportunity, because as Greg was mentioning, when you get these sort of tropical convective flare-ups, they're intrinsically creating an opportunity to better predict when they happen. On the same side of that token, though, there are cases where they significantly degrade the skill in global numerical weather prediction. And so there are times when the dynamical predictions are far less skillful, even at week 2, than a simple linear inverse model. And so that's where the wrestling, I think, is interesting, and something that it's going to require improvements in our NWP, right, at that point, whether it's data assimilation or physics inside of the global NWP to make better forecasts there. But yeah, I'm on the short range convective scale, I'm a pretty big believer that we're going to have a hard time creating better CAM based, we're at kind of where we're at. And you're going to see now these storm-based ensembles coming online, whether it's href v2, scrapping the NAM and going to a big FV3-based, convective suite. We're not going to get any better. In fact, there's going to be short-term reduction in skill because our microphysics packages in FV3 haven't caught up yet with WRF.
Yeah, I agree wholeheartedly, just from when I was working with MPAS and doing the 5-day convective forecast verification with that, of just seeing what the kind of skill ceiling was with that, and then including the ensemble approach. Like at the end of the day, like what you were saying, if the observations are going to be the key to go there. And so continuing with that and what you were saying about, it really depending on the modes of predictability being favorable. My last question for you is, obviously it's well known, and you mentioned that summertime severe weather predictability is just absolutely like trash. And I've seen several stuff from even I think like Ryan Jewell and a few others, like showing that even the skill of STP in June, July, August is just abysmal. Yep. So from your perspective on the more climate side, do you think that's solely due to the mesoscale subtleties and influences of that season, or do you think there are other teleconnections that just aren't being looked at and can be leveraged?
Generally speaking, when you get in that time of the year, the MJO is not going to have a significant influence. There's, the spring predictability barrier that you're up against, but generally across the CONUS, it's just the issue of outflow boundaries from previous convection that just basically, you don't talk about throwing a wrench in a forecast, right? On a storm scale, just improperly assimilate an outflow boundary. Okay. That propagates through, you're done. And so when we talk about, increased window of skill for opportunity, these are typically early season, March, April, beginning of May, strongly synoptically forced regimes that you're going to have skill in. And then when you get to June,
all out the window.
Forget it. Yeah. And
awesome. Thank you very much. And
yeah, no problem. I will say, like the FV3 point that I mentioned, like we have, as a community, we've decided to go with FV3, or at least NOAA has. We basically got a new vehicle. We have a new engine in the car. And now we're going to probably go backwards for a couple of years, figuring out how to tune the suspension, kick the wheels, figure out the brakes, right? Because we've forged ahead with the core, but none of the microphysics are ready yet. And so we have a long way to go. And unfortunately, you know, all of this increased skill that everybody wants to see from FV3 is not happening because
Got to work out the kinks.
not ready yet. So I'm a believer of FV3. I think the dynamical core, the solver, it's fast. I'm cool with it. I'm good. I'm like, you're not going to convince, I like MPass, but you're not going to, you know, I can be convinced that this is the way to go in terms of computational efficiency, but we shouldn't expect better forecasts from UFS, this framework, until all of these tunings, you know, imagine how long it took for WRF to get to this particular place. It's going to take a while for the community input to get to where we need to be to make FV3 a viable, you know, convective scale candidate for replacing something like the HER. It's just the nature of the beast of what we've done. So I'm still a huge user of WRF and even, you know, you guys using CM1, et cetera. So
Awesome. Well, thank you very much, Victor.
yeah, thank you all. Any last minute questions?
Everybody's all zoomed out.
Yeah, we all have Zoom fatigue. All right, well, follow up. If not, let me type in the chat here really quickly. My email address, if any of you, you could just, of course, you're all very capable, I'm sure, of using the Google, but to save you, if you want to connect offline, there's my email address and feel free to reach out. But otherwise, thank you so much for attending. I sure wish I could go out for a beer with you all now, but we're all going to need a couple shots in the arm before that happens.